Composite transformations is just doing multiple transformations to the same equation. For example, to get from here to here, you'd have to transform it in this order. If you're having trouble with the ordering, the order of operations may help you. The highest priority transformation should be done first. Be careful with questions like these. You can try them out for yourselves first. I'll reveal the answers in a couple of seconds. Okay, I'll tell you that these are not the correct answers, because these transformations would end up with this result. You can rewrite one of the equations to make it easier to find the answer. These are the correct answers. Let's say that you have the value x, and you want to turn it into a positive number that still has the same distance from 0. You could do this by squaring x and then square rooting it, since any squared number will be positive, and square rooting it will revert it back to its original magnitude. The shorter way of writing it is this, and it's pronounced mod x, or the modulus of x. The modulus function makes any number positive. Here's a more formal way of writing it down. For this video, I'll just compress it into this, since putting a sign in front of a 0 doesn't change it. If we look at the graph of y equals mod x, you can see that you'll have two x values going into the same y value. So if you had a question like this, then these would be your solutions. When you take the modulus of something, the part of the curve that goes below the x-axis gets folded upwards. You can think of these kind of curves as a combination of multiple other curves. These curves each have their own equation and their own domain. The placement of the modulus sign also matters. Take these two graphs as an example. For more complicated questions like this, you can use the modulus definition to split this up into two separate equations, and when we solve each of them, we get the answer. The domains are really important because without them, you might end up using values that aren't in the domain as your solution. For example, here, the two curves don't intersect, therefore there should be no solutions. However, if you don't take the domains into consideration, you'll end up with what I like to call ghost solutions, solutions that should be rejected. The easiest way to do this question is to just sketch it without the modulus sign, and then fold whatever lies below the x-axis upwards. However, this only works if y is inside a modulus sign. As questions grow more complicated, it's best to build the sketch up step by step. So for this example, I would sketch it in this order. For this one, sketching it step by step won't work. Instead, we'll have to figure out what curves y is made out of. Split the equation up to deal with each modulus. Use the modulus definition on each of them to find their components. Group the domains to get 3 unique regions for y, and find the equation of y at each of these regions. This is the information that you'll need to be able to sketch the graph. The graph will look like this. You can see how it's made up of multiple curves, each occupying a unique region in y. The solutions to this question will be the intersection between these two curves. From sketching their graphs, we can tell that there will be two intersections, one over here and another way up there. The first intersection is with the folded part of the quadratic curve. I'll also get the x-intercepts of the quadratics, so that we know what x values we're expecting our answer to be in between. The next intersection is with the unaffected part of the quadratic. Again, use the x-intersection to determine the correct x value, and there's your answers. When dealing with questions like these, unless you want your brain to get fucked, I seriously recommend that you sketch graphs to help you solve them. Here's the algebraic solution to show you how much more complicated it is. Solving this question is pretty much the same thing as before, except there's an additional step because you're dealing with inequalities. Again, it's advisable to do a sketch. By comparing the y values of each curve, the inequality will only be true at these areas. Work out the intersection points and use them to work out the answer. Here's a worked examination question you can try. I'll give the solution out in a few seconds. Okay, A convenient way of doing both a and b is to use the modulus definition. Using our answers from a and b, we can sketch the graph of f. The line of symmetry lies over here, which you can get by taking the average of these two values. From the graph, you should be able to find the range of f. F of x equals 4 at these 2 points. Use the appropriate values of f of x to find the x values of those points. From the sketch, we can tell that f has a many-to-one mapping, therefore it has no inverse. To end the video, here are some trick questions. Pause the video and try them out for yourselves. For the first question, the modulus of x will always be positive, so it'll never be less than a negative number. For the second question, the modulus of x will always be greater than a negative number, so x can be any real value.